Today is lesson 5. We're looking at exponential and logarithmic equations. First, let's explore exponential equations. An equation that's written in the form of y equals b to the cx power, where the exponent includes a variable, is known as an exponential equation. In our first example, we have 5 to the 2x equals 37. So to be able to solve this for our variable x, we're going to take the log of both sides of the equation. So our first step is to take the logarithm of both sides. And then our second step, to isolate things, we want to use the power property of logarithms. And in the power property, we can take this power 2x and use it as a factor in front of our logarithm. So that's using the power property. And right after that, we would want to isolate the 2x. So we want to divide both sides by the log of 5. So we're going to divide by log of 5. And that will help us to isolate that variable on 2x. So we're isolating the variable. And then in the next step, we're going to use our calculator and find a numerical value for log 37 divided by log 5. So to be able to do that with our calculator, that's going to be simplifying the log expression. And then to divide by 2, we'll solve for x by dividing by 2. And we found out that x is about 1.12179. Then this lesson also considers logarithmic equations, and a logarithmic equation is any equation that includes a logarithm involving a variable. So in this example, we're going to have log base 3 of x equals 5. And if we use the definition of logarithms and convert the logarithm into an exponent, we could rewrite the log as an exponential equation, which is what we've done. The base raised to the power of 5 is going to be equal to our number, and our number is x. And we're trying to solve for x. So we rewrite the log as an exponent. And then using our calculator or just our brains, we can say 3 to the 5th is 243. So the number x is 243. Solve for x. So log base 3 of 243 is equal to 5 because our logarithm is an exponent. So you can check that with your calculator. In example 1, we're going to practice these things. So solving 5 to the x equals 125. The easiest way to handle that is to recognize that if our bases are the same, then the exponents are equal. So we can rewrite 5 to the x is 125 by rewriting 125 as 5 to the 3rd. So here we have the bases are the same. So when the bases are the same, the exponents are equal. The bases are the same, so our exponents are equal. And we've solved for x in that case, and x is 3. So x is 3. 5 to the 3rd power is 125. In example B, you need to be a little bit clever. We know that 27 can be rewritten as 3 to the 3rd power, and 81 can be rewritten using 3 for the base as 3 to the 4th power. Then using properties of exponents, when you raise a power to a power, you multiply the exponents. So 3 to the 9x power is equal to 3 to the 4th. And just like in example A, when our bases are the same, our exponents are equal. So 9x must be equal to 4, and that happens when x is 4/9. And then similar to example B, we're going to do the same thing with part C. 4 to the 2x plus 1 power is equal to 4 to the 5th. That might take you a little bit to calculate, but 4 times 4 times 4 times 4 times 4 is 1,024, which means that 2x plus 1 is equal to 5. So when 2x is 4, then x is 2. And using that concept all the way through on example 1, when our bases are the same, then the exponents are equal. Moving on to example 2, in part A, we have 3x is equal to 17, and I've got the same situation we had earlier. We need to get the x out of the exponent area, and to do that, we would take the log of both sides. Then that allows us to move this x as a multiple in front of our log, so x times the log of 3 is equal to the log of 17. And if you want a decimal approximation, be sure to grab your calculator, because solving exactly the log of 17 divided by the log of 3 is the value of x, but we want a decimal answer in this case, so we can check that. And using our calculator, we get 2.5789. And you can go back and try this number into our exponent here. So 3 to the 2.58 power is going to be very close to 17. In part B, we've got 5 to the 2x equals 135. So similar to part A, we want to take the log of 5 to the 2x, but if you take the log of the left, we need to take the log of the right, and then our 2x is going to be a factor in front of log of 5, and then isolating the 2x term, we're going to have the log of 135 divided by the log of 5. And then to solve for x, we want to divide also here. We want to divide out this 2. So dividing by 2, then using our calculator, the log of 135 divided by 2 times the log of 5. So you want to put that in parentheses on your calculator. And the value for x is a little more than 1.5. And then once again, you want to multiply this number times 2, and then use that answer for our exponent for 5 to the power, and see that we get very close to 135. Then for part C, following the A and B versions, if we take the log of 8 to the y minus 3 power and take the log of 26, then that entire exponent, y minus 3, that entire thing becomes a factor of log of 8. And you can isolate the y minus 3 by dividing both sides by log of 8. Log 8, and then adding 3 to that. So before we add 3, we want to get a decimal approximation for this portion, the log 26, divide log 8, and that's about 1.5668813. And then add 3 to both sides. So we've got 4.568. And again, I would remind you to use this value for y, go back to the original equation, and find y to this power minus 3. So 8 to the 1.56 power should be really close to 26. And be sure to check your work there. In example 3, I'm using my TI Inspire, and I want to solve my exponential equation 2 to the 3x power equals 9. I want to solve that by graphing. So to solve that by graphing, the first thing I did in my Y1 window is I graphed the graph 2 to the 3x power, and notice how I adjusted my window on x from -4 to +4, and I adjusted my window on y from 15 to -4. And then I graphed the right side of the equation. So if 2 to the 3x power equals 9, I drew the graph of y equals 9. And next I found the intersection using that intersection feature, and I found out that the graphs intersect when x is about 1.06, roughly. And you can solve using a table, and similar to the same thing, I used the table setup and adjusted that setup to start at x equals 1, and I did delta table at 0.01, so 1/100th, and found on my table at 1.05, the graph was very close to 9. At 1.06, it was a little past 9, so somewhere between 1/500ths and 1/600ths, the graph intersects. In example 4, we're looking at a real-world example. If the world's population can be modeled by this equation, P equals 6.72 times 1.014 to the x power, and P represents the population in billions of people X years after the year 2000, we want to use that model to find the population in 2013. That means when T is 0, that represents the year 2000. So to calculate 2013, then T would have to be 13 in 2013. So all we need to do is calculate the P of 13 by using the formula 6.72 times 1.014 to the 13th power. And here you can see that our growth rate, if you move that decimal over 2 places, our growth rate's about 1.4%. So carefully with your calculator, the P of 13 is about 8.05, and I've got mine giving quite a few decimal places. So if this answer is in the billions of people, then we got 8.05 billion people in 2013, or if you wanted to say 8,051,238,429 people in 2013. So either one would be an okay answer. 8.05 billion is another way to answer that. In part B, the year when the world population is about 9 billion, we could do this one of 2 ways, either graphically or algebraically. I'm going to model algebraically by saying I want the intersection where 9 is equal to this power equation, 1.014 to the x. So to solve for x, first we would isolate the term that has the variable, and I could do that if we divided both sides by 6.72. And then the next step would be to take the log of the left, and I'm going to calculate 9 divided by 6.72 is about 1.339286. So we did this arithmetic here. And then taking the log of that side, 1.339286, 0.014 to the x power. Then we can bring the x down in front and divide by the log. So if we divide this log by this log, we would have the log of 1.339286 divided by the log of 1.014. And that answer is going to be about 21.012. So we're very much into the next year here. So in the year 2021 and a little tiny bit, so maybe in the year 2022, the population would reach 9 billion. So we got to go into the 22nd year in order for that population to reach the 9 billion mark if the model holds true. In example 5, we're going to solve two equations. You notice that we're having the common log here. So in both cases, we have base 10, and 10 to the 1/2 power is going to be our number. So the number 2x plus 1 is 10 to the 1/2 power. And the 1/2 power is the same as the square root. So isolating the variable side on the left, 2x is equal to the square root of 10 minus 1. And if you calculate the square root of 10 minus 1, that's about 2.16228. Then divide both sides by 2, and we get 1.08114. And then you can, again, check with your calculator, log base 10 of 3. So we're going to take this line right here and add 1 to it. 3.16, so 3.16 log base 10 should be close to the 1/2. And you can check that out. In part B, we're going to divide both sides by -1 to get rid of the negative. And that would equal +1. And then again, we got base 10, so 10 to the first power is equal to our number, 3 minus 2x. And if we add 10 or subtract 10 from both sides, that gives us 7. So 7 is equal to -2x. And divide both sides by -2, we get -3.5. Or you can write that as a decimal, either one, whichever you prefer. And again, I would recommend going back and checking that your answer works in the original equation. Here in our last two examples, we're going to solve using the properties of logs. So in example 6, we've got the log of x plus 9 added to the log of x. And that property, when you have the log of one number added to the log of another number, you can multiply the two numbers together to combine the logs. So the log of a product is equal to the sum of the two logs. By multiplying, we've got x squared plus 9x. And again, notice I have base 10. So the log base 10 to the first power is equal to our number x squared plus 9x. In this case, we want to get all the terms on one side of the equation and use our information like a quadratic equation. And you can factor the trinomial because factors of 10 times 1 will add up to 9, and we would multiply 10 times -1 to give us -10. So our first solution is x equals negative 10. And our second solution is x equals positive 1. Now, if you go back up here to our original equation, you can put negative 10 here, and I'd be taking the log of a negative number. And here we would do the same thing. So those two are not allowed. We can't take the log of a negative number. This is extraneous. And I'm reminding myself about the log. Just think about the log equation, the graph of a log. You know, our y-axis is a vertical asymptote here. So there's no logs of negative numbers in the domain. And x equals positive 1 is our only possible solution. Then for example 7, again, I've got to combine the left side, so the log of 6 minus the log of 3x can be combined using the property of logs. The difference of two logs is the quotient of the single log. So our number, 6 divided by 3x, simplifies to be 2 divided by x. And again, we're thinking about base 10, so log base 10 to the negative 2 power is going to be equal to 2 over x. Now, 10 to the negative 2 power is 1 over 100. And solving for x is going to be 200. And then again, I would recommend that you check your work. So checking into the original, log of 6 minus log of 600. I want to know, is that really equal to negative 2? And if we use those same properties, 6 divided by 600 is equal to log of 1 over 100. And here you can see that property. 10 to the negative 2 power is definitely equal to 1 over 100. So it is true and it checks. And we have finished lesson 5.